Okay, in this lesson we're going to look at solving a linear quadratic system of equations graphically. We've looked at solving systems of equations that were linear last year when you looked at a line with another line. This year you're going to look at a line with a curve, and that curve will either be a quadratic relation, so a parabola, or it may also be a circle. So just a reminder of what a quadratic function looks like. It looks like y equals ax squared plus bx plus c. And this is when the function is in standard form. If it is in vertex form, you may see it as a k x minus d squared and then plus c. Okay, so you may also see it in vertex form. Then you have a linear function, which usually you will see in slope-intercept form, and that's y equals mx plus b. So in case you forgot what a system of equations is, a system of equations consists of two or more equations that are considered together. So last year you saw things like 2x plus 3y minus 5 equals 0, and then you had another equation like 3x minus 3y plus 2 equals 0. And then what your goal was to look at these two equations, or these two linear functions, and then find the point of intersection between the lines. So similarly, we're going to look at solving a linear quadratic system, and again, we're going to try to find a point of intersection between a line and the curve, okay, or points of intersection. So a solution to a system of equations must satisfy each equation in the system. Or in other words, the solution or point has to exist on the graph of each of the equations. So for example, if you have the point of intersection between a parabola and a line, these 2 points that I'm highlighting have to exist both on the line, and they also have to exist on the parabola as well. And you can see that those 2 points actually exist on the line and on the parabola. If I draw another point and I draw it on the line, you'll notice that this point here does not satisfy the system because it only satisfies the line. It doesn't exist on the graph of the parabola. Okay, so that's what it means by a solution to a system and it satisfying the equation in the system. So a few reminders from last year. First of all, linear systems of equations may have no solutions, one solution, or an infinite number of solutions. And if it has no solutions, what that indicates is that you have a pair of parallel lines. Okay, so when you had parallel lines, you knew that the lines would never touch, and so you would have no solutions. You could also have one solution if the two lines that you're looking at actually intersect, and so we would call these intersecting lines. And you would have an infinite number of solutions if you had two lines that had the exact same equation, and essentially what happened is that those two lines would overlap each other, and so they would actually be coincident lines or equivalent lines. Okay? And some of the things that you know about each of these lines are that for parallel lines, the slope was the same and the y-intercept was different. Okay? For intersecting lines, most of the time the slope was different and so was the y-intercept. The only time the y-intercept was the same is if the point of intersection between the two lines happened to be on the y-axis. And then for coincident lines or equivalent lines, because the equations of the lines are exactly the same, both the slope and the y-intercept were the same for both functions. Okay, so those are some things from last year. Unfortunately, this year, because you're looking at a line and a curve, you won't have parallel, intersecting, or equivalent, because one of the equations you're looking at is the equation of a line and the other one is the equation of a curve, either a parabola or a circle. Let's look at our first example. And we're going to try to solve the following system of equations graphically. In the first example that we have here, we have a quadratic function, so y equals x squared plus 2. So parabola shifted up 2 units. And the second line is, the second equation is the equation of a line. And this is in slope y-intercept form. And you can tell it's a line because the highest exponent you have on x is just an imaginary exponent of 1. So if I graph these two to try to find the point of intersection, what I'm actually going to do is graph the parabola first. And because the only transformation to this is a shift up 2 units, I can actually use the step pattern to graph the entire function. If there were several different transformations, I would have used mapping notation, but because there's only one transformation to it, I can use step pattern to actually graph it. So I'm going to use a scale of 1, and I'm going to start by plotting the point at the vertex, which is at 0 and 2. So 0 and 2 is the vertex. And I'm going to move over 1, up 1, go back to the vertex, over 2 and up 4. And then I think that's as many points as I can fit. And I'll do the same thing on the other side. And don't forget to extend your graph since you are looking for a point of intersection, and also label your graph as well. So there's my first function. The second one is the equation of a line. The slope here is 1 over 1. And the y-intercept is equal to 4. So I'll start by plotting the y-intercept at 4. And then I'm going to use the slope to help me plot a few more points. Okay, so I'm going to rise 1, run 1, rise, run, rise, run, rise, run. And I'm going to draw a line. And you want to try to draw the line accurately since you are looking for a point of intersection or points of intersection. And again, don't forget to label it. So this is y equals x plus 4. And you can see that we have 2 points of intersection in this case. We have a point of intersection here at 2 and 6. And we have a point of intersection at -1 and 3. Okay, so as my concluding statement, what I could say is, therefore the solutions to the system are -1 and 3 and 2 and 6. So we have 2 points of intersection, or we have 2 solutions to the system. Or in other words, we have 2 points that satisfy the system of equations. So therefore, the solution to the system, or the solutions to the system, are -1 and 3 and 2 and 6. Okay, in the little box here, we are asked to check our solution for part A. So if you remember from last year, whenever you are checking your solutions, you need to do a left side, right side check. And this time, we're going to be doing a left side, right side check for both points, since you're checking to see that both points satisfy both equations. So what's going to happen is we're going to check each point, and we're going to make sure that that point satisfies both the equations. So I'm going to do a left side, right side check for the first point and both the equations. And then I'm going to do a left side, right side check for the second point in both the equations. So I'm just going to do that on a separate sheet of paper. And so what I'm going to do is check. And I'm checking the point -1 and 3. And then I'll do a separate check afterwards for the point 2 and 6. Okay, so what I need to do is a left side, right side check in both the equations to make sure that left side equals right side for each of these equations. So the first equation I have is y equals x squared plus 2. So y is on the left side and x squared plus 2 is on the right side. And the second equation I have is y equals x plus 4. So y on the left side, x plus 4 on the right side. Okay, and so what I'm going to do is I'm going to substitute in my values of x and y for my point to make sure that the left side equals right side for each one of these. If left side is equal to right side, then that means it satisfies that particular equation. Our goal is to check if it satisfies both the equations. So let's start with the first one. I'm going to plug in y equals 3, and that's all I can do on the left side. On the right side, I'm going to plug in x, and I get -1 squared plus 2. And I know -1 squared is 1, plus 2 is 3. So in this case, you can see that the left side and the right side are equal to each other, and it satisfies the quadratic equation. Okay, so this point exists on the graph of the quadratic function. Let's check if it exists on the linear function. So I'm going to do the same thing. I'm going to plug in my y value, which is 3, and then move over to the right hand side, and I have -1 plus 4, which I know is also equal to 3. So it also satisfies the linear function, which means this point exists on both the graphs, and so this is definitely a point of intersection between the two functions. Let's check the last one. So the second point I had here was at 2 and 6. And so I'm going to do a left side, right side check for the point 2 and 6. And so I have to substitute in the point into both my equations. So I'm going to do a left side, right side check into both of the equations. And the left side of the first equation or function was y. The right side is x squared plus 2. The other equation is y, and then x plus 4. So I'm going to substitute in the point again. Y is equal to 6. And x is equal to 2 squared plus 2. 2 squared is 4 plus 2 is 6. So again, this point exists on the graph of the parabola. And now we want to make sure it also exists on the graph of the line. And if it does, that's another point of intersection. That's another common point between the two functions. So y is equal to 6. And x is equal to 2. 2 plus 4, which also gives me 6. So that means since left side equals right side for both points in both functions, then those two are the points of intersection, and they are also the solutions to the system.